Welcome to our technical design and flight readiness review. I'm Francisco Bueno, and I'm the team captain of the Aircraft Lab SUAS team from St. Louis University.
My name is Fauzan. I have been working on the SUAS competition for 2 years. I am the navigation and controls lead.
My name is Walid Abdullah. I'm a first year and I am the ODLC member.
My name is Imran Saeed and I am the ODLC team lead.
My name is Alejandro Crespo and I'm part of the performance and structure team for the past year.
Hi, my name is Melanie Reem and I'm part of the performance and structures team for this past year.
Hi, my name is Kabir Huja and I'm a team member of the navigation and control team.
Hi, my name is Elizabeth Wangley and I'm on the performance and structures team.
We investigated the SUAS 2023 competition requirements. We designed our UAS accordingly.
Aircraft Lab SUAS is composed of 3 teams: Navigation and Controls, Performance and Structures, and ODLC. The aerial system is a fixed-wing UAS which is made out of composite materials. We come with a Pixoc autopilot and Jetson on board. The airplane is operated by a certified RC pilot and a ground station operator to send mission profiles through telemetry.
We used a 1080p GoPro which records at 60 frames per second and process them inside a GPU-integrated Jetson Nano. We generated synthetic data and trained the YOLO machine vision model on our data. Once YOLO identifies a target, we locate it by comparing GPS coordinate inputs the moment when the target is in the middle of the frame.
For the airdrop, the team designed, manufactured, and tested a controlled descent vehicle to deliver the payload to a target safely and accurately. This vehicle has glider characteristics and it will be towed from the main aircraft. A gripper mechanism was created to drop the glider and it was placed on top of the airplane. After getting released, the glider will perform a loitering maneuver for the first part of its journey and analyze the optimal path to a target. The pros of this approach are the ability to integrate a gripper into the main aircraft, and it has minimal effect on the aircraft performance. Additionally, a controlled descent vehicle minimizes the physical damage to the payload, and it can maneuver while gliding to the desired target. The cons are limitations to delivering 5 payloads back-to-back. According to the competition rules, every time the main airplane lands to reload the payload, it would need to redo the mission. This would cause our team to take longer to finish the mission.
We communicate from our ground station to our primary UAS and drop vehicle using Holy Bro telemetry radio, which has a frequency of 915 MHz. The telemetry radio is expected to have a range of 3,000 feet. To perform manual flight, we need a transmitter and receiver. We use Futaba T10J for our transmitter and Futaba R3008SB for our receiver, which both has a frequency range of 2.4 GHz. The transmitter and receiver is expected to communicate in a range of 3,000 feet.
CFD analysis was done at 0 angle of attack straight flight in order to visualize the flow to determine immediate shortcomings, if any, of the current design. This preliminary analysis was performed to aid us redesign areas which were coming. There seems to be no downforce caused by the horizontal tail dust. A negative angle of incidence must be added in order for a high pressure area to be generated on top, giving us downforce and better control when the elevator is deflected. The main aerial system was designed and manufactured by one of the senior design team, 2021 and St. Louis University. The airplane design was validated using advanced aircraft analysis software and SolidWorks flow simulation. AAA was used to calculate the dynamics of the airplane. The following table shows the results obtained from AAA. For the manufacturing part of the aircraft, multiple processes were performed to fabricate each component of the airplane. For the fuselage, a custom mold was cut using a CNC machine. The fuselage is composed of 3 layers of fiberglass. They were epoxied together and a vacuum seal approach was performed, creating even pressure throughout the mold. The wings are made out of insulation foam, fiberglass, and plywood ribs. The foam was cut using a hot wire CNC machine, and the ribs were fabricated using a laser cutter. There is a carbon rod going through the quarter core of each wing and an anti-torsion wood spar that goes through the middle of the wing.
The propulsion system is electric-based, and it is powered by a LiPo battery, which is 10,000 milliamps. The motor chosen for our aerial system is a A60 5X4V with an 18-inch propeller diameter, and it is controlled by an ESC. The motor was tested in our facilities using a thrust stand to understand its performance during flight. Those tests were conducted by increasing the PWM signal of the motor until the max thrust was calculated. A load cell type S was used to read the thrust produced by the motor, and the motor max thrust was 30 pounds, and it was reached when the PWM signal was at 1,780.
We're using Pixoc 4 Mini as our flight controller hardware and the PX4 Autopilot as our flight controller firmware. PX4 Autopilot is an open source flight controller. PX4 Autopilot has position, attitude, and rates controller for a fixed-wing UAS, which is the type of UAS we are using for the competition. PX4 Autopilot is capable of waypoint navigation. We can adjust the acceptance radius of the target waypoint to 25 feet. To plan our flights, we're using Crew Ground Control software, which is running in a Windows 10 OS laptop. Crew Ground Control is capable of planning waypoint navigation missions and uploading them to the Pixoc 4 Mini. We developed an obstacle avoidance algorithm that will avoid other UAS by circling them. This algorithm is done in real time. This is done by, number 1, generating a circular boundary when another UAS is detected, and number 2, generate additional waypoints surrounding the circular boundary.
One of the alternatives considered was the payload delivery. We would drop 2 gliders from the main airplane using a release system underneath the wings. This approach would affect the aerodynamics of the main airplane. Another option was the type of tail configuration of the main airplane, such as a T-tail or a V-tail. It could improve the dynamics of the airplane. We also considered autopilot as a flight controller firmware, however it wasn't user-friendly. Lastly, another option considered was a Sony RX100 V2 camera for ODLC.
This challenging mission required us to create a robust system capable of meeting the requirements of the competition. The first step taken to ensure a safe flight is a pre-flight checklist. The team meets 2 days before the flight day and goes through 41 bullet points that cover electronics, battery logs, structure, tools, and vehicle checks. There is one more checklist that is done before takeoff. All of this is done under the supervision of the team captain. Another risk is the manufacturing part of the airplane. We deal with composite materials, and it is essential to have a protocol. We ensure to provide adequate equipment to handle those materials. Moreover, our system carries 2 LiPo batteries on board every flight. Understanding that they could get punctured due to a bad landing, the team is prepared to mitigate any fires at the flight field. Additionally, a special box container is prepared for the transportation of those batteries. The last step taken is loss of connection or power. The pilot has experience with zero-power landings. Also, our airplane's flight controller will loiter around the last connection spot if we were to lose ground control. If no control were to get recovered, the plane will perform a mayday maneuver to the ground.
We successfully generated training data and verified the bounding box's coordinates. We also streamed from the camera and saved the video locally inside the Jetson Nano, but only at 360p resolution. We expected the Nano's GPU RAM to be sufficient for training the YOLO model, but this was not the case.
Unfortunately, we are still in the phase of testing for our airdrop vehicle, so we are unable to perform the airdrop mission of the competition.
To test our communication performance, we flew the longest and furthest flight. Our UAS flew for 19 minutes and 46 seconds, ranging to 1600 feet. Throughout the flight, there was a signal connection every 0.1 seconds. This results in 1187 signals sent. From those signals received, 37 of them were lost.
Our UAS underwent 12 successful flights, with a total of flight time of 82 minutes. Our UAS is capable of flying for 13.2 miles. It has a minimum of 125 feet turning radius. It has an angle of climb and descent of 20 degrees. It can maintain above 200 feet AGL, and it can perform waypoint navigation with acceptance radius of 25 feet. Throughout all this flight, we were able to observe how every component on the aircraft interacted within them and the environment, what helped us to improve components like the landing gear. With all these goals achieved, we continue to challenge ourselves, working on an object detection algorithm that will be incorporated into the UAS.
We made 4 different flight plans and tested 5 waypoint navigation flights. Out of 94 target waypoints, 68 were successfully followed. Based on the flights, we've observed several limitations. If we set the speed of the aircraft to 33 miles per hour, we will observe bad waypoint navigation results. Same results were observed when we set the acceptance radius to 16 feet and when we flew a waypoint navigation missions with sharp turns.
We developed a path planning algorithm and tested it both in simulation and flight test. The path planning works well in a simulated environment because the acceptance radius of the simulation target waypoint navigation is close to 0. In reality, the waypoint navigation of our UAS only works and has been tested for 25 feet and 32 feet acceptance radius. When we tried a 16.8 feet acceptance radius, the autopilot sent unusual roll set points. We were unable to test our UAS detection algorithm, and therefore in the end, we think the obstacle avoidance algorithm is not ready for this competition.
We have been recording data from 12 test flights. At these flights, we first validate manual control, then progress to autonomous waypoint navigation. To prepare autonomous waypoint navigation, we perform autonomous loiter and auto-tune processes. We also perform 2 throttle failure tests so that our safety pilot and ground station operator are ready when throttle failure occurs during the competition. During these tests, we have also been keeping a log of 2 batteries that are on the plane, the 10,000 milliamp hour battery for the motor and the 2,700 milliamp hour battery used to power the Pixhawk. These observations were used to determine the safe lifespan of the battery for flight use.
conclusion, we're ready to compete in the SUAS 23 competition. We performed numerous testing, including manual and autonomous flight. We provided sufficient proof of safe flight and good communication performance. However, in the competition, we won't perform ODLC, payload delivery, and obstacle avoidance mission. We'll see you at the competition.